What's up, guys? So I have not had time to edit my YouTube video for this week. So you know what that means? Today, we are an educational channel. Let me show you guys the finite element method, FEM. I don't really know where I'm going with this video. I'm just making a video to get a video out. But let's say, we have a beam and it's got all these forces on it. P0 is a force, and it's got this moment on it. M0 is a twist. F0 is a distributed load. And so obviously all this pushing and twisting on the beam is going to make it bend, right? And twist. We want to find the exact values of those. Like at here, what is the displacement? Like this. And what is the rotation? Which is just twist displacement. So that's the entire idea. We're looking for displacements. And if we know the displacements, we can also find other things such as the forces or shear forces and moments on the beam. What we know from science probably is that this equation is how a beam deflects. V is the displacement, and this is a differential equation. So we probably know F, and we know D. D is the, I think, flexural rigidity of the beam. That's just stuff you know based on like what the beam is made out of. And that just means you have to solve for V. Solving for V is tricky though. So we have a shortcut, the finite element method. I think there's some assumptions made here to get this matrix equation. I think in some cases the K matrix will be different as it'll be added with something else, and that's called an A matrix, I think. But the point is here, UE is basically V in this case. There is a point where that change from V to U makes sense, but that's all you have to know. U are displacements. The U's are displacements. There's many U's. This is a vector. There's many U's inside of here. And KE, FE, RE, those are things we know, and those are things we just plug in. And after that, we're able to solve for UE. And let me show you how we know what goes into K. What goes into K, for example? And so this is just for this beam drawn out over here. For an example, I'm going to be using 3 elements to split the beam up. You see this element and this element. You see I've split them up into equal lengths there. And that means K will be a 3 by 3 matrix. But first of all, that means that there's going to be 3 points where we're looking at or 4 points where we're looking at the displacement. How do I want to say this? Well, yeah, that's pretty much why K is 4 by 4. You see? 1, 2, 3, 4, 1, 2, 3, 4. F is a four-dimensional vector. There we go. And so anyway, you fill in K by knowing the properties of the beam here and the length of the element, which is here, and then this is just given to us by theory. These are all the same for each of the K's, and the only thing different for the K's are going to be the H's and the properties of the beam, the flexural rigidity, if that happens to vary in this beam. And that's literally it. Just plug and chug those. Same thing for the F's, you plug and chug those. F1 is it's the distributed load. And in our case, we have a constant distributed load of F0, and that's what I will plug in here. F2, and that should be F3 and H3. Oopsie, that has major implications. Save that. You can see here that there is no distributed load in the second and third elements. So those are eventually, I'm going to plug in 0 into F2 and F3. And you also plug in the H's for each element. And so once you know those, then you're looking for the R's. The R's are the reaction forces and moments. Let's take a look here. We obviously know that P0 and M0 are acting on the third node. And that's what we're going to plug in eventually into the equation right here. Those are the values for the force and the moment. We know that there is a force reaction and a moment reaction at the wall, because if you push something and it's in a rigid wall, then it's going to resist that because the wall makes the beam not want to move. Newton's laws. And so those are just left empty as R11 for the force and R12 as the moment, and we're going to be solving for those. And the way I understand it is, let's take this second node for, actually no, it's even cleaner. Let's take this final fourth node as an example. There's going to be a reaction because this roller restricts it from going downwards. However, there's nothing resisting the beam from twisting, so there will be no reaction moment. There's nothing to resist the twisting of the beam, so it'll just twist freely. From that, we can say that the reaction moment is 0 at that node, and that's why there's a 0 here. And there is not a 0 here. There's the R for the third element, third node. Yes, third node. That's something I explained very badly, but let's just take one element. It looks like there's 2 nodes, right? No, in this case there's 4. It's 1, 2, 1, 2, 3, 4. And what that looks like is displacement, rotation, 1, 2, displacement, 3, rotation, 4. And those are cool, and you're going to do that again once you get into higher degrees of freedom, because you're going to be looking at displacements longitudinally or in the third dimension. But that's what that is, and that's why that thing was 3. Oh, hi, Clint. You have any, you like beams?
I got 3 Doritos, Locos, Tacos.
Nice. And so from there, we have 1, 2, 3, 4, 5, 6, 7, 8 unknowns and 8 equations. Let's just review that again. This is where I'm solving. So let's take a look. This is unknown, 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 this is unknown. That's 8. And what we know from linear algebra is if you have 8 unknowns and 8 equations, then you're probably chilling. I hope those things highlighted. I know my screen cap sometimes doesn't like to record mouse inputs properly. But once we solve those, we have what we need. One more funky thing is if it asks for things in the middle here, right here, that is R13 plus R21. Third node of the first element and the first node of the second element. So if we want to find R13, then we just solve the local system. We've been solving the global system. That's why we added the K's and the F's together. You can see here, putting the K's and the F's together to solve the global system. The local system is pretty much solving the matrix equation for one of the elements and only one of the elements. And that's where we can get R13 as shown here. That's all I have. Yeah.
Finite element, what's that?
Method?
Method. For what context? Like subject?
In general.
Shem?
that.
Wait, we talked about that in mech design. Tiny little.
Yeah, that's what I was talking about. You
Yeah.
set up all these equations,
We solve them a bunch for a bunch of little small elements.
and it's just a shortcut to the answer. And you know that there's going to be error involved, but you can calculate that, probably.
For
Mhm.
the front wing, I'm acting as if the wing elements are cantilever beams, and the downforce is a distributive load. And it's like, okay, based on that distributive load, what's the moment at the structure?
That's really cool. And you guys hear that? Ashton's working on a formula car, and he's just treating the wings. Like, let's just pretend this is a front wing. That's a front wing, and that's the nose, and pretend the nose is just rigid, and you're just looking at forces on the wing relative to the nose.
And that makes sense because downforce is basically like a distributive load.
Yeah.
So
Yeah, downforce is a distributed load. Your foil looks like this.
yeah,
And as you go along, each element will produce a different amount of downforce because there's a different amount of pressure gradient, right? Is that how it works?
yeah. But I was talking about in terms of if you're looking down towards the
Oh,
front wing.
also looking down?
So each element makes a certain amount of downforce, right?
Yeah.
So
Like
you can,
this element and this element?
Yeah. So I'm treating as if, say this makes 10 pounds of downforce, this element. I'm treating it as if it's 10 is a distributed load of 10 pounds per length, whatever this length is.
Oh, gotcha.
So you get a distributed load of that, and then each of them will make a different moment about that point.
Yeah.
So your shear moment diagram, remember that?
Mm-hmm.